Hi everyone, welcome back. This is a continuation of Chapter 5, more specifically a continuation of Chapter 5.1, so this is Part 2. So what we haven't covered yet in 5.1 is this key concept here, so we're going to describe how to determine whether outcomes are significant, whether they're significantly low or significantly high. So in talking about significance, you've seen this before, so we're going to go over again this range rule of thumb. So in this range rule of thumb, we have a figure like this. So values that are significantly low are ones that are the mean, or mu, minus 2 times the standard deviation, or sigma. So looking at this figure here, here's our mean, here's mu, then we go over this minus 2 times the standard deviation. So any values less than that are significantly low. Then conversely, we have our mean here. We're going to add 2 times sigma, or 2 times the standard deviation. Then any values that are beyond that are ones that are significantly high. That just leaves this area here, so anything that's between mu minus 2 sigma and mu plus 2 sigma, these values are not considered significant. Another way to think about this is if the value is close to the mean, then it's about close to the other values in that data set. So unless a value is way below the mean or way above the mean, then it's considered not significant. And actually in statistics, we want our data to lie in this range, so being significant isn't necessarily a good thing. Let's apply the example we've been working on in 5.1 so far. So we found that when tossing 2 coins, the mean number of heads is mu is equal to 1.0 heads. We also found out the standard deviation for this same example is sigma is equal to 0.7 heads. We can use this range rule of thumb we just went over to determine whether 2 heads is a significantly high number of heads. So let's talk about the solution here. So using the range rule of thumb, we know that any values that are mu plus 2 times the standard deviation or greater are significant. So first we need to determine what mu plus 2 times sigma is. Well, we can plug in our values that we know. We know we calculated mu is equal to 1.0, sigma is equal to 0.7. So mu plus 2 times sigma then, using our order of operations, we're going to multiply 2 times sigma first, then add mu. So we get 1 plus 2 times 0.7. That's equal to 2.4 heads. Going back here really quickly, the reason we're doing mu plus 2 times sigma is because we're curious if our value is significantly high. If we were asked if that value is significantly low, then we do mu minus 2 times sigma. Okay, so we got this value here of 2.4 heads. What that's really saying is significantly high numbers of heads are going to be 2.4 and above. So another addition to this figure is that values over here are significantly low values if they're less than or equal to mu minus 2 sigma. Then these values here are not significant. Then these values on this side are significantly high if they're greater than or equal to mu plus 2 times sigma. One thing these additions to this figure do point out is that when the value is less than or equal to this value, then it's significantly low. So it can also be equal to be considered significantly low. In the same respect, values that are significantly high can be greater than or equal to mu plus 2 sigma. So back to our question here, we're asked whether 2 heads is a significantly high number of heads. Well, we figured out that this value here is anything above 2.4 and above is significantly high. So if we were asked if 2.4 heads is a significantly high number, that answer would be yes, because it is greater than or equal to 2.4, where we got 2.4 as mu plus 2 times sigma. But we're not asked about 2.4, we're asked about 2. So based on these results, we can conclude that 2 heads is not a significantly high number of heads because it's definitely not greater than or equal to 2.4. So going back to this figure, we have 2.4 and above is significantly high, then 2 would fall in this range here. We know it falls in this range here because our mu value is 1, so it's going to be between 1 and 2.4. So this was determining significance with this range rule of thumb. Another way to do this with identifying significant results with probabilities specifically is something we have seen before as well. So significantly high number of successes, if you remember seeing this, it's when X number of successes among N trials is a significantly high number of successes if the probability of X or more successes is 0.05 or less. So to do this, we'd figure out the probability, then we'd see if it's 0.05 or less, and then we can determine, based on that value for the probability, if the number of successes X that went into calculating that probability is a significantly high number or low number of successes, which we'll get to on the next 1 or 2 slides. In other words, when X is a significantly high number of successes, then we get a probability value when X is plugged in here or more. That probability value is less than or equal to 0.05. You may have noticed so far that most of our probability values of X are greater than 0.05, but we have done this. We have calculated the probability for different X values now, especially now that we've gone through the beginning of 5.1. As mentioned previously with a slide that you've seen before that looks just like this, the value of 0.05 is not absolutely rigid. We could also look at probability values that are less than or equal to 0.01, for example. Let me talk through this example too. So if we obtain a probability of the specified event occurring using this X number of successes and using N number of trials, we get a probability value of 0.0000003. That means that the number of successes used to calculate that probability is a significantly high number of successes. I showed you this slide too, but I want to talk through it again now that we've gone through the beginning of 5.1. So for example, if 100 births, where N is the number of trials, where N is equal to 100, so N is the number of events or the number of trials, then we get 75 girls that are born. In this case, 75 is our X number of successes. It's sort of the same thing as thinking about when we flipped a coin twice, then we could have 0, 1, or 2 number of successes. Here we have 100 births rather than 2 coin tosses. So among the 100 births, we're looking at 75 girls were born. That's really our variable here. So P of 75 is equal to 0.000003. Let's say that's what we got for our probability value. That means that 75 girls is considered significantly high, because certainly this probability value here is less than or equal to 0.05. In the same way, if we have 100 births again, that's the number of events, that's the number of trials, so that's our N value. Then if we're looking at the probability of getting 55 girls specifically, so 55 would be our variable X. X is also considered our number of successes. Essentially, that's how many times is that happening. So going back to the coin toss example, we had 0, 1, or 2 number of successes, because that's how many heads we got when we tossed 2 coins, either 0, 1, or 2 number of heads. That's the same thing as 0, 1, or 2 number of successes. So here for our N value and here for our X value, our variable P of 55 girls is not significantly high because we determined the probability was 0.184. 0.184 is definitely not less than or equal to 0.05. Going here again to the significantly low number of successes, it's really similar to what we've been talking about. Here we have X number of successes among N number of trials. But if this X number of successes is going to be considered significantly low, then calculating the probability with this X number of successes or fewer needs to equal 0.05 or less for this variable X to be considered significantly low. In other words, X is a significantly low number of successes, that's our variable, when P of X or fewer is less than or equal to 0.05. Again, I put the same caveat that 0.05 is not set for every different probability scenario. It could also be 0.01. For the example here for a significantly low number of successes, if we obtain a probability of a specified event occurring is again very low, lots of zeros here, then the number of successes used for that event to calculate the probability is significantly low. It's a significantly low number of successes to be specific. Okay, so both with determining significantly high or significantly low number of successes, we need to calculate the probability, then we need to look at that probability value and see if it's less than or equal to 0.05. Further on in the semester, we'll get more into assumptions and are we proving our assumption false or true? Still related to determining significance, if under a given assumption, the probability of a particular event is very small and the outcome occurs significantly less than or significantly greater than what we expect with that assumption, then we need to look at what assumptions went into that calculation. And then we'll likely conclude that that assumption is probably not correct. To give you a little bit more context on assumptions, for example, when flipping a coin, we assume that by chance we're either going to get heads or tails. If the mass was slightly off with that coin and we didn't know it, and our assumption is that purely by chance we'll either get heads or tails, well, if we get an outcome that doesn't quite make sense, then maybe that assumption that the penny was a normal penny wasn't correct. So maybe there was some deformation in the penny causing the probability to not be exactly equal, where we get half heads and half tails. Typically when flipping a coin and we're assuming that it's 50-50, either we'll get heads or we'll get tails, that's a pretty safe assumption to make. There are some assumptions, however, that won't be as obvious. So again, we really need to be critically thinking about what all assumptions are going into our calculation. And if something is slightly off in our finding, we need to go back and really assess each assumption that went into our probability calculation. Let's use an example here on gambling. So this one, be a better. So you have $5 to place on a bet in a casino in Las Vegas. This is hypothetical, of course, unless you're of age to gamble, but you're not going to gamble, you're going to save that money instead. I know. So you have narrowed down your choice to one of two bets. Here we're asked to determine the better bet. The first option is that we're playing roulette and we're betting on the number 7. The second option, we're going to play craps and we're going to bet on the pass line in this dice game. Let's talk about this roulette option first. So we're going to bet on the number 7 in roulette. We've talked about roulette before, where there are 38 different slots, 38 different options. So let's set the stage here. So if we bet $5 on the number 7 in roulette, the probability of losing $5 is 37 out of 38, because we can only get number 7 in one of 38 of these slots. So then the other 37 are going to be that we don't get 7, we lose. So then the probability of making a net gain of $175 is 1 out of 38 chances. If you recall from an earlier lecture, the prize is $180, but this includes your $5 bet, so the net gain is ultimately $175. This was discussed in full detail in 4.1, so go ahead and check that out if you need a refresher on this. Then continuing with part A, we're going to find our expected value, remember that terminology, if you bet $5 on the number 7 in roulette. The reason we want to find the expected value here is because we want to compare that for roulette and craps and decide which is ultimately the better bet. Let's continue with part A here. So We're going to organize our data in a table, and we'll start doing that on the next slide. You also have this table in your student outline. The first thing that comes with setting up this table is we need to decide the probability of getting 7 out of these 38 slots and the probability of getting not 7, so this complement here. Remember that complement probabilities need to add up to 1. So the probability of getting 7 we just talked about is 1 out of 38. The probability of not getting 7 is 37 out of 38. Right? It's all the other different slots that we could land on. From the example we previously did with roulette, we have a casino payout of 35 to 1. 35 is how much we're profiting, where 1 represented how much we're betting. So all of this needs to be multiplied by 5 because we're betting $5. So when we're betting $5, we're going to multiply 1 by 5 and 35 by 5. So we could profit $175 when we bet $5. Again, this was fully explained in 4.1, so go back and see that if you need more explanation. So this is when we would win, and we have 1 out of 38 shot to win this. When we're going to lose, which is 37 out of 38 chances, then when we lose that $5 that we bet. So we represent this as a negative $5 because it's a loss here. Let's start filling in numbers in the table. So we're going to set this up as our event, where our event is either that we lose or we win. In the event that we lose, we're going to lose $5. In the event that we win, we're going to gain $175 as our net gain. Remember, because we had to bet $5 initially. So when we bet $5, we win $180, but then we subtract that $5 for a net gain of $175. So in the next column over, we need to describe the probability of these values here. So the corresponding probability is going to be 37 out of 38. The corresponding probability here is 1 out of 38. How do we find the expected value? What is that the same as calculating? Hopefully you're thinking along the lines of the expected value is the same thing as calculating the mean. So we need to calculate the mean for this case. Remember our formula for the mean, so we need to take x times p of x and then sum all of these values. So let's go ahead and do that. Here we have an x value of -5. Our probability of x is 37 out of 38. Here we have an x value of 175. So the corresponding probability for that is 1 out of 38. So for each row, just like we did for the coin toss example, we're going to then sum up these values to get our mean. When we sum up these values, we get a value of -0.26 or -26 cents. So when we calculated this, we calculated both the mean, which is the same thing as calculating the expected value. So to summarize here, we made this table. Then we multiplied x times p of x for each case. Then we summed these up, and we got an answer here of -26 cents. The way of thinking about this is that for every $5 bet on the number 7 in roulette, you can expect to lose an average of 26 cents. This 26 cents is our mean. It's also our expected value. This 26 cents is also then representative of when we bet $5 on the number 7, it's what we'd be expected to lose. For betting scenarios, this is likely always going to be a negative number and not a positive number. But we saw earlier the mean is not always a negative number. The expected value is not always a negative number. Here for this betting scenario, it is a negative number. Let's go through part B now. So deciding if playing roulette or playing craps is better based on the different bets that we wanted to do. So for craps, this is information you'd have to be given. So if you bet $5 on the pass line in this dice game, the probability of losing $5 is 251 out of 495. Then the complement to this, the probability of making a net gain of $5 is 244 out of 495. Just as we thought for roulette, we're thinking about the net gain here. So if you bet on the pass line and win, the prize is $10. but you had to bet $5 initially, so your net gain is still $5. So we found the expected value for roulette. We're also going to find the expected value, or the mean, the same thing, for craps. Then we're going to decide which of the two bets is better in the sense of producing a higher expected value. That's what we want to determine in the end. So let's calculate this expected value for this crap scenario. So to set this up, we need to know the probability of winning, and we need to know the probability of losing. We just learned these on the last slide. Then we need to set this table up again. So we have our event of either losing or winning. In craps, when you lose that $5. In craps, when you win and you bet $5, the way this bet was placed, you also have a net gain then of $5. It sort of makes sense that this is not a huge net gain because these probabilities aren't that much different. It's almost 50-50, obviously not quite 50-50. So far from what we know, we're going to set this table up where x is equal to minus $5 or plus $5, and then we have our probabilities of losing and winning. Let's continue on to calculating that expected value. Maybe you'll pause it and calculate this before me. So when we're calculating the expected value, we're also calculating the mean. We're using that equation here, so x multiplied by p of x. Then we total all these up, we sum them. So when we do that, x times p of x for this row is negative $2.535. When we do that for this row, we get negative $2.4646. We sum these. So that uppercase sigma notation, and then we get this sum here of negative $0.07 or negative 7 cents. Negative 7 cents is our mean. It's also our expected value. Here's that notation I was talking about. So here's that uppercase sigma that indicates we're going to sum all of the values here. Putting that into words now, for every $5 bet on the pass line, you can expect to lose an average of 7 cents. So now we have the expected value of roulette and we have the expected value of craps based on the two ways we could bet in either one of these games. Let's talk about the interpretation here and answer our question. So for the $5 bet in roulette, this results in an expected value of negative 26 cents. The $5 bet in craps, however, is an expected value of minus 7 cents. So piecing this together, because you're better off losing 7 cents rather than 26 cents each time for every time you bet $5, the craps game is a better bet in the long run. This is even though the roulette game provides an opportunity for a larger payoff when playing the game only once. But if we're playing this over and over and over again, then we'd rather lose 7 cents each time than 26 cents. Okay, so with this example, we went through, we figured out the expected value the same way we calculate the mean. So we set up that table of our x values and our p of x values. Then we summed those up to get our expected values. We compare those now. So then we can answer this question that betting on craps is a better idea because we lose less money each time we bet. This is the last slide now in 5.1, so I'll see you next time for 5.2. As always, let me know if you have any questions at all, and I'll see you next time.